Good evening. First of all, I apologize if you can hear an annoying low-pitched hum in the background. Without wanting to bore you with details, let me say I've tried my best to minimize it using the methods I have on hand, but it's possible that it may still be audible. Anyways, tonight let me go on a tangent with you. This was extracted from a forum post where it is not that relevant, and making a separate thread also didn't seem appropriate because to the users there it's probably old news. However, because I found it quite interesting, I decided to make a video about baby's first assembly optimization. Now, we're currently at the Commodore Basic Ready prompt. You've likely seen this before, but if we enter sys820, we suddenly find that our C64 has become a lot more polite. This is just a little language model I've whipped up. Let's greet it. See, it agrees. We can make engaging conversation with it, and it maintains proper conversational tone. I can give it commands, and it will obey them immediately. I can even let my cat walk across the keyboard. Moo, I'm his cat. And somehow it already knows his name. But as nice as this constant flattery is, this whole your lordship thing is wearing on me a little bit. If only the C64 could be a bit more concise. Would you look at that? It can! Well done, C64. Proper punctuation matters. Now, I'd like its confidence just taking that compliment without any sort of fake modesty. Anyways, let's tell it a dark secret and see how it responds. Just like the people on the bus. But, you know, with hindsight, I do kind of miss the old C64. The one who would respect my aristocratic lineage. The one who was courteous. And just like that, we've put it in its place. Let's share another dark secret. And I think this conversation has just about run its course. So let us indicate this with a simple full stop. Yeah, that happens. Anyways, okay, now that we've looked at this, let us type another sys command to pull back the cover and see what makes it tick. What makes it tick? What makes it tick? I'm keeping that in. Anyways, so here's the source code for this model. Let's quickly go over it. So we start, this assembles to the cassette buffer, or really it starts at the 8 unused bytes before the cassette buffer. But anyways, first of all we clear the screen, so we just use a kernel subroutine for that. Then we load a pointer to a string and use the basic interpreter's string out function, and this string message, you can see it's down here in the data section, it just contains yes. Then we check, using the bits instruction, a memory location called flag byte. And what the bits instruction does, in case you don't know, is it performs a logical AND between the accumulator and the memory location while discarding the result. So effectively that sets the 0 flag, depending on whether the result would have been 0. And it also copies the 2 most significant bits into the negative flag of the status register for the most significant bit, which would be the sign bit, and the second most significant bit, so bit 6, into the overflow flag. In this case, we use it to copy the most significant bit into the negative flag, so that we can then branch on minus to skip this. So if the flag was cleared, then the negative flag will also be cleared now. So we go here and we load a pointer to the message called kowtow, which is just the your lordship, and jump the string out again. And then we continue by printing the message end, which is just the full stop and carriage return. So as you can see, if the flag bit in the flag byte was set, we just skip the your lordship thing. Okay, then we call a little subroutine I've made called getCar, which all that does is call a kernel subroutine for the screen, a basic interpreter subroutine for the screen editor. It sets y to 0, so that's just some housekeeping. It stores in the text pointer, and then it jumps to the car got subroutine in 0 page to read the first character of input. That's all this does. Then what we do is we compare this first character of input to the letter C. Now don't let this fool you. While this looks like the lowercase c, that's because of the character set that Turbo Macro Pro uses. It's actually, if I use Shift Commodore, it is actually the uppercase C. So this is just a quirk with the lowercase character set. Now, if the accumulator was not equal to C, then it branches ahead to no toggle. It then checks if the accumulator was the full stop. If that was also not the case, then it goes back up to the loop. Otherwise, it ends the program. If it was equal to C, then it loads the accumulator with the value hex 80, and that has the most significant bit set, which is our flag bit. It then XORs it with the flag byte, which effectively toggles the most significant bit of that and then stores it back. After that, it does an unconditional branch to the loop. The reason this is unconditional is because if the comparison results in an equality, the carry will always be set. Because, well, the carry will be set if the accumulator was greater or equal to the comparison value, and well, if it was greater or equal and we know it was equal, then that means the carry will be set. If the carry is set on greater or equal and we know it was equal, it will be set. Okay, so now while this is a fairly standard, I'd say textbook method of toggling a flag, it does seem a bit disproportionate that toggling a single bit in memory and then testing it would take a total of 10 bytes. So toggling takes 6 bytes, checking it takes 4. This is for something else. It doesn't have anything to do with the toggling technically. Anyways, so I was thinking about how to optimize this. Well, so the first approach. Oh, and by the way, before we do this, let's see how much space it takes up before this. So it goes up to hex 383. So I don't care how much that is, but the point is that's where it goes to right now. Now, we just said the carry is always set when you come here, and we only care about the most significant bit of this flag byte. So instead of explicitly loading the accumulator with the value hex 80, what we can do is we can rotate right, and what that does is it shifts the entire accumulator to the right, so every bit moves one bit to the right. It moves the current carry into the most significant bit of the accumulator, which is the one we care about toggling, and then it also pushes the least significant bit into the carry, but we don't care about that effect right now. Although it will alter the carry here, so in this case this is fine, it's still set, but just be aware of that. Now, this only takes 1 byte, so we've saved 1 byte in total. So if we assemble this, it now goes up to hex 382. We can quickly test this. I'm not going to do as long of a demo as previously, but just to show you, this does still work. Okay, let's end this and return to Turbo Macro Pro. So now our flag toggling takes 5 bytes, checking it still takes 4 bytes. That's better, but we can still do better. When you think about it, if we only care about setting a single flag, what we really care about is not so much any particular bit being toggled. We care about a toggle between 0 and non-zero. So that means we could just use any non-zero value to toggle this. Now, as it happens, we know that the accumulator at this point always contains a non-zero value. So instead of toggling only the most significant bit, what we can do is we can just delete this line entirely and just XOR the entire value C with the flag byte. One caveat of this, though, is that in this particular case, our effective bit mask value no longer has the most significant bit set. So that means this wouldn't work anymore. Now, if A contains a value, if we know A to contain a value here that has at least one bit from our bit mask value C set, then this would still work, and we just have to exchange this branch if on minus for a branch if not equal. However, assuming we could not rely on this, I don't know about it honestly at this point, we can just load it. At least in this case we can, because we know that we can afford to clobber the accumulator at this stage. So we just load A with the flag byte, and if anything is set and if it's non-zero, we branch ahead. That means we've now saved another byte, bringing the toggle code down to 4 bytes. The checking code remains at 4 bytes. Granted, we do rely on the ability to clobber the accumulator, or another register would also work. But still, the point about this video is that often you can optimize a lot if you account for the state of the machine at any given time. Now, if we assemble this, you'll look and see that it only goes up to hex 381. So that's 2 bytes saved now. So if we leave and we type sys820, we now see that this still works. Okay, let's go back to Turbo Macro Pro. One more thing to bear in mind here is that this does rely on a known initial state of the memory address, because assuming your memory address started out as containing a non-zero value or a value not equal to this bit mask, then of course it would never be 0 if you toggle it. In this case, the value I chose to use contains the last load and load/verify flag. So that means if the last load instruction was just a normal load, it will be 0. If it was a verify instruction, it will be 1. But I think it's reasonable to assume that for our purposes this is just 0, because how often do people use the verify command? But it's something to bear in mind. And of course, realistically, knowing a byte to be 0 is going to be a lot likelier than knowing it to be exactly your bit mask value. Anyways, so now we've just got 4 bytes for toggling the flag, but still, even so, we're still taking 4 bytes to toggle this flag. That's better than 6, but I think we can do better. See, if only we didn't have to do this laborious first XOR, then store it back. If only there was some read, modify, write instruction that would allow us to do this in place. Well, when you think about it, there is one, or technically 2, and that is the increment instruction. Let me just write it down here. Or the decrement instruction too. Whenever that happens, this inherently toggles the least significant bit. Now, one problem with this is, of course, that it's not quite that easy to check for the least significant bit. So, sadly, unless you knew the accumulator to be exactly 1 at this point, in which case you could do a bit or an AND, depending on whether you can clobber the accumulator. Assuming you didn't know this to be the case, or you'd know this not to be the case, the next best thing you can do is to do a logical shift right. Now that takes 1 byte, so sadly we don't get to save 2 bytes, we only get to save 1, but still, and then we branch if carry set. So basically what happens now is every time we go here, we increment the flag byte, which toggles the least significant bit, and then later on we load it, we shift this least significant bit into the carry flag, which fortunately does not change the value in memory. You could also do this in place, but of course then that would destroy the flag, because now you've shifted it for good. So you need to take this detour, sadly. Anyways, and then you branch based on the state of the carry flag. So that saves another byte, which brings us down to 380 in terms of our end address. And once again, just to confirm this still works, it says yes, lordship. We can type in anything. We can use the C to change it into more concise mode, and then we can change it back into courteous mode. Okay, that still works. Right, that's as efficient as I managed to get this flag logic. So we did sadly increase the size of the flag checking logic, but we saved 1 byte overall. Of course, it depends on how time critical this is as well. Assuming this ran in very time critical code, you might not want this, but then again, I was optimizing for extreme space constraints and time wasn't that big of an issue. Okay, there's one more optimization that doesn't actually have anything to do with the flag, but you know, I did it in this whole process, and that's that this control flow is a bit suboptimal, or rather you can optimize the control flow to save more bytes. Specifically, what we do here is we check if the accumulator is C. If that is not the case, we branch ahead. Otherwise, we increment the flag byte and branch back up to the loop. The problem is that this takes 2 additional bytes for an unconditional branch. This is already optimized compared to a jump instruction, but still, we can, in this case, and this is another one of those points about thinking about the state of the machine. You know, in this case, however, you can optimize control flow to save yourself one of those branches. Specifically, what do we want to do here? If we toggle the flag, then we toggle the flag, and then we branch back up to this loop. So we want to execute this code next, always. Well, why not just do this before the loop here? We say toggle flag, then we increment the flag byte. So we just move this up here. Let's also mark it with its size. Then we remove this unconditional branch and instead just keep this conditional one, and instead of branching over something, we instead branch if equal to toggle flag. So now we've saved the 2 bytes for that unconditional branch, and we still have the same logic. One caveat of this though, this works perfectly fine and you save 2 bytes if this is in a place where you can't accidentally execute it. So for example, before the entry point. In this case, this actually comes after the entry point, and depending on how critical it is that this flag not be disturbed, which will of course depend on your concrete use case, assuming you don't want it toggled every time somebody starts the program, what you can do, you can still save 1 byte, and that is by having this be preceded by a byte to C. So that takes 1 byte, obviously, and it's the bit abs opcode, okay, bit abs. So what that does then is, we already know the bit instruction, so basically what this does is, after you've called the CLS routine, it will then see this as a bit absolute instruction, and because this is 2 bytes, because it's in 0 page, that means it will basically see this as perform an AND and discard the result between the accumulator and whatever address these 2 bytes represent. This is a fairly standard 6502 optimization. If you want to quickly skip something without having to spend the 2 bytes for a full branch, you can just put a bit instruction in there, because usually this is okay. I suppose unless you really need the flags to stay consistent, then you might have to come up with another solution. A store instruction, for example, if it's memory that you can afford to modify. But anyways, I think you get the idea. So this now means that in total we've saved one more byte by removing this unconditional branch and only keeping the conditional branch. Now, if we assemble this again, you'll see we only go up to hex 037F, so we've saved a fourth byte. Again, this doesn't have anything to do with the flag toggling per se, I just thought it was interesting. And just to confirm, it does still work. Alright, so what was the point of this video? Well, I guess the point was to show you that the textbook method for optimizing something, or for doing something, even if it's a fairly optimal textbook method, can still be improved further if you're willing to account for the state of the program at the time of execution. Mainly it was just because I spent such a long time optimizing this flag toggling and I was a bit proud of how small I managed to get it, so I figured I'd share it with the world. But again, to the people on the forum, it's probably not that interesting, but maybe it is to you, and if not, well, you know, then I failed. Anyways, perhaps if you have any ideas how one could optimize this further, I would of course love to hear them, or if you have any corrections, as always, you know, I'm very open to them, and I hope this did not put you to sleep, or if it did put you to sleep, that you at least had nice dreams about very efficient 6502 assembly code. I know I do. Okay, well, that's it. Goodbye.